Yes, please.
Thank you very much. Thanks for joining me. For the next 25 minutes, I will guide you through my presentation, indeed about streamlining the ADAS verification through an integrated software-defined vehicle framework. So let's first talk about some trends in the ADAS space. First of all, and we all know this, of course, there's a focus on increased robustness of the ADAS systems. That is mainly driven by the regulations, but of course also by customer expectations. There's more functionality. We move from level 2 to level 2+ to even level 3 or 4 systems. But very recently, we also see that there's quite a heavy emphasis on reducing cost and significant cost reductions. I mean, I'm hearing even 40–50% budget cuts for ADAS development. So that's very significant, and yeah, that's something that we have to deal with. And at the same time, there is a reduction. There's time pressure on the time to market. And that's very well stated here with the chairman of the board of BYD, who says that today it's not about the big fish eating the small fish, but it's actually the fast fish eating the slow fish. And so it's all about time to market with less money and with more complexity. So how does the industry deal with that? One answer is actually the software-defined vehicle. So why is this an important development in the automotive industry? Is because on the one hand side, it allows for new application areas. ADAS AV is one of them, but also, as we were hearing before, AI platforms, but also over-the-air updates that are prolonging the life cycle of the products. And on the other hand, it's also allowing new business models. We've heard from several OEMs that are putting more and more subscription models in cars, and that's all in the area of trying to find more monetization of the product. With the software-defined vehicle, you also see at the bottom of the slide that the electronic architecture is changing. So where in the past software and hardware were connected to each other, you see that in the modern cars there's a more zonal architecture that was also mentioned before today. So more software is disconnected from the hardware and is more running on high-performance compute systems. And actually ADAS is one of the, I would say, larger software systems that is in the vehicle. And it's a very important software function from the one hand side because it requires actually high compute functionality. So that's also the reason why it moves to those high performance compute systems. ADAS is very complex. I mean, you need to deal with all the different sensor systems, data fusion, and it also has to be taking decisions in real time. But at the same time, there's also high opportunity for monetization. I mean, people are willing to pay for the higher level of ADAS systems. So that's also important for the automotive industry. So the high-level question is, how can you optimize a software-defined framework faster and reap the benefits of new business models? So the answer that we have from Siemens looks a little bit like this. Many of you know Siemens from the PLM systems. So that's with our Teamcenter approach, we manage the entire product lifecycle of products. And with the software development and software-defined vehicle approach, we also add this new layer on top of our PLM foundation. And how does that look like? How does that software-defined vehicle framework look like? So now first it starts, of course, with product requirements and application requirements. So we have our PLM systems and ALM systems managing that. In previous presentations today, you also saw the SysML activity, so that's more on the system modeling that you see on the side. And then we move into the architectural and design processes of the mechanical components, the electrical components, and the software components. And while we develop them, of course, there's the continuous integration and continuous validation activities. At some point when you are, let's say, 90% sure of what you have developed, whether that's working fine, you move towards more hardware in the loop and vehicle in the loop systems. And you basically want to deploy your system only with 100% design confidence. So then you do your over-the-air update, maybe some shadow testing before you actually release it, and then you start collecting data again, and then that entire loop starts again. So within Siemens, we see actually 3 different personas. So the first persona is the person that does the mechanical development. So that's actually the development of the vehicle itself, the mechanical systems, the actuation systems, also the powertrain. On top of that, you have your electronics hardware development, responsible for the electronics design, the networking of the system, but also the compute systems. And on top of that, you have your software development. And the interesting thing, of course, of the software development is that basically never stops. So once the car is released in the market, you continuously continue to do your software development and your over-the-air updates. So how does that software development look like? So of course, again, it starts from the requirements. You start writing your code. But at the same time and in parallel, you actually start collecting your scenario database. And I will come back to that later, but there's multiple different ways how you can build up that scenario database. And while you're writing your software, you do your verification loops. So that's typically the model-in-loop systems first. And at the bottom, you see your digital twins that you develop in order to test against that. So digital twin of the world, of your environment, digital twin of the sensors, but also digital twin of the vehicle, the actuation systems, and the powertrain. And then later in the process, you comply the software, and then you run them on an AUTOSAR virtual ECU with software in the loop. And then later on, as I said before, it's basically hardware in the loop testing that you do. So let me explain how we support this entire process with the different tools that we offer to the market. So the first thing is, how do you build up actually that scenario database? So there's multiple different ways to fill your database. So one source is the scenarios from regulations and from the standards. Another one is from requirements. Most of you are also collecting a lot of real-world data from which you collect the scenarios. There's also synthetically generated scenarios, and of course there's also public databases that you can use, for example, accident databases. To give you an example of how to extract scenarios from standards and from regulations, but also from requirements, we're working together with a company called Diontech, and they are basically able to generate scenarios from text. And you see here an example where they are taking specific standards with large language models. They convert that into different requirements and text, and they are able to generate an open scenario file that you then can download into Simcenter Prescan, and you can then run that scenario. Of course, this is an example of one scenario that you then run in Prescan, but you can imagine that in that way you can very easily capture scenarios from standards and requirements. Of course, there's always the possibility to build manually scenarios based on your ODD. For that, we have our Simcenter Prescan GUI, which is very easy to very quickly build very specific scenarios. And we have pre-made models of the environment and vehicles and sensor systems in the vehicle to build actually your digital twin there. The other way to fill your scenario database is what a lot of people are doing, is by actually starting driving around and capturing a lot of driving data. And here you see our process to convert driving data and put it into a database, making it also searchable. So the tool at the bottom, you see that we offer a cloud-based interface towards the engineers, in which you can very easily search specific scenarios. So it automatically makes a catalog of the different scenarios, cut in, cut out scenario, emergency braking scenario. And you can also specifically specify your own KPIs, and it automatically will pop up with the scenarios that have not met your requirements. And then you can further dig into the details. Once you have selected scenarios of which you say, hey, these are interesting ones, you can select them and you can store them in your database. You can store them for replay. But one of the things that we're also working on in collaboration with some partners like Antimotion, who's also here, and here technologies for the map data, we can convert these driving logs into digital twins, very accurate digital twins, that you then further can process also in our Simcenter pre-scan program for further testing and analysis. Now, this example of safe and unsafe, and known and unknown scenarios has been on the slides already many times today. With the previous examples that I presented in order to fill your database, you typically find the known scenarios, safe or unsafe, but you typically have not captured the unknown scenarios. And that is always the difficulty, to find the unknown, unsafe scenarios. And for that we have developed an automatic methodology that generates unsafe, unknown scenarios. You typically can do that in two ways. So one way is the actor focus method. So there you take an existing scenario and then you start changing parameters in order to make that scenario critical. So it can be, you're crossing an intersection and then you start changing the speeds of the other actors in order to make the scenario critical. That is actually how most of our competitors also are doing it. But we have come up with a very unique other method, which completely generates new scenarios that you have not seen before, but are possible and are plausible as well. So we have a patented approach there that optimizes the scenario generation towards critical scenarios, but also very probable scenarios. And in that way, the projects that we have run with our customers, it always shows that we always have been able to find scenarios that people have not been thinking about. And then in retrospect, they say, yeah, this was typically a scenario that we did not think about, but it is indeed possible, and we should add it to our database. So this is a very, very nice way of completing your scenario database according to the SOTIF standard to minimize the amount of unknown, unsafe scenarios. I'm not going to say that we will find all the scenarios that are possibly out there. There will always be kind of residual risk, but I can assure you that with this methodology, the residual risk that you have is minimized. Once you have built your software and have filled your scenario database, you typically want to do continuous integration loop. Typically, you do that on the cloud. We can run massive amounts of simulations. And we have set up continuous integration pipelines to automatically, when the code is uploaded, you automatically run these continuous integration pipelines for example, on the AWS cloud, to run through these massive amounts of scenarios to validate your software. And as I said before, when you are confident about your software and your functionality at some point in the process, you start to compile your code, and you want to validate also whether that code runs on the hardware. And also here we have a very interesting offering with our Pay360 offering, which basically provides a kind of virtual car to every engineer's desk. So we use virtual ECUs, virtual hardware, to which you can actually run your compiled code. The interesting thing here is twofold. On the one hand side, you have you can start building code for hardware that does not exist yet. So you don't need to wait until the actual hardware is available, and you can already start testing your code against new chipsets, for example, that will become available. That is one reason why people do this. But the other reason is also that even if you have the hardware available, hardware rigs are very expensive and are typically not available in very big quantities. So with virtualizing the hardware, you can actually also again run it on the cloud, and you can actually have multiple instances of your virtual car, have that available at every engineer's desk, so you can run your software against that very easily. The benefit of this system is that it is able to handle mixed reality. So you can have everything virtualized, but you can also start moving, the moment you build up your car, you can start moving more and more real hardware into it, and that can even be also, so part of it can run on the cloud, part of it can be run in your lab, and it's completely synchronized and working in real time. So it's a very powerful way of moving gradually from full virtual towards full real in the end. Hardware in the loop, as I said before, can exist of various different flavors. And here we have this matrix where we go from everything virtual to everything real, and every flavor in between. And you can have your vehicle, for example, real, or your sensor real, or your ECU real, or only the ADAS controller real. I mean, or every mix that you can think of here. And with the Pay360 setup, you can really mix and match all these different activities. And one example I wanted to give for you is what is actually boxed here, is the projection hardware in the loop. Typically, it's well known for camera systems. So you have a real camera that's watching a virtual projection on a screen. But in collaboration with Keysight Systems, we have actually built this also for a radar system. And I don't know if you visited the Keysight talk earlier today, but Keysight built this radar scene emulator that basically is a kind of screen, a pixel screen. I learned this morning that they call it Rixel, where they can provide real radar images to a real radar. And by combining that system with our physics-based sensor simulation system, Simcenter Prescan, you can run very interesting setups where you have very complex environments, in this case with a bus and a pedestrian and a bicyclist, and you can actually see the radar measurements coming towards you, and then, of course, based on these radar measurements, you can test and validate if your perception systems are picking up the right topics. And because we have this physics-based radar pipelines, we could actually relatively easily connect to the Keysight system that normally is being used to actually replay data, but with the simulation system next to it, you can actually start running it in closed loop, so it has more potential and more usage for your system. Yeah, that brings me actually to my last slide. So with Siemens Accelerator platform, yeah, we provide you true software-defined vehicle expertise, specifically also in the ADAS domain. As I mentioned before, we integrate it seamlessly in your PLM and ALM systems, and we will do virtual validation. We accelerate the hardware and software co-development. I think it's a very important topic in software-defined vehicle. We have seen many examples in the last few years where that interaction didn't go well, and that the software that these engineers were building was actually too heavy for the compute systems that were ordered, and that when the integration went together, yeah, the systems were not performing well. And by virtualizing the hardware and doing that co-development in a virtual environment, yeah, you can prevent these type of mistakes. Of course, as Siemens, we are very much for open platforms. So we are also part of the ASAM committee. We very much support open industry standards. So all the software that we build adheres to these industry standards, such that we have a very modular approach, and we can very easily integrate our software solutions in existing pipelines that already exist. And with that, we make it also future-proof for all your ADAS and EV development. Yeah, and last but not least, yeah, we very much believe also in SaaS, in cloud-based applications, but we also know that many of you still rely on on-premise solutions. So that is, of course, also there we have flexibility, and we have also mixed environments and even multi-cloud environments that we can deal with. So, yeah, with that, I would like to thank you for your attention. And yeah, there's room for questions, obviously, but I would also like to ask you to come to our booth later on and continue the discussion.
Thank you, Gwen.
Thank you.
Questions? Yeah.
Gwen, thanks so much for your presentation. Armin Engström from ABL. So I don't know if I understood it correct, but your answer to credible sensor models is go for hill? Or do you also have different approaches to this very obvious question, credible or validated sensor models?
Yeah, no, it's a very good question. Obviously, we provide virtual sensor models, but I fully agree with you that that is pretty hard to validate the physics-based sensor models. We do that, so we have validated sensor models, but yeah, the validation typically is done in lab environments, and yeah, that has some reference. But of course, if you run, especially with radar systems, if you run them in real environments, I mean, the behavior can still be quite different. So yeah, a lot of our customers and a lot of the industry still rely on hardware-in-the-loop setups. That's one reason. The other reason is also because, and that was also mentioned before, I think it was by ANSYS actually this morning, is that it is not straightforward to build very accurate sensor models. Also because the sensor suppliers are not always opening up their IP. And yeah, one way to circumvent that is, of course, to use hardware-in-the-loop systems. So yeah, it's definitely still and will be for the long future still one of the steps that you have to do in your validation cycle. Yeah.
So now it's hill, and in future it's going to be completely physical sensor models. Because I think if you go for hill, as you explained, then you're later. So you only get parts of the time to market advantage that you have been proposing in the beginning of your presentation.
Yeah, the earlier, the more you can shift left and the more you can do in virtual validation. Of course, it is an investment to build your virtual models, but yeah, you will gain from time to market and co-development between your hardware and software. Yeah.
Thanks so much.
Yeah, thank you.
Okay, another question? Yeah, please.
Thanks for your nice presentation. My name is Philipp Rosenberger from Percival. So thanks, Armin, for asking my question, my first question on credible sensor models. Second question is it also possible, as you mentioned, the ASAM community to plug in, for example, sensor models from different suppliers via the open simulation interface?
I would say not yet plug and play, but I think it's a very good initiative from the market that also that interface is becoming more standardized. I think there's still a way to go for all manufacturers to adhere completely to that interface, but we are definitely following it very closely. And I think it's a new interface that is actually forming, but I think it's an important one. And yeah, I think the standard is not mature yet, so it still has to be evolved a little bit further. And then, yeah, the different suppliers also have to adhere more and more to the standard. But I would say it's a new standard that enables to make more combinations of different vendors possible. Yeah.
Okay. Thanks for your answer. I mean, as I'm in the change control board of the standard, probably we can talk afterwards.
Yeah, no, let's do that. Oh, absolutely. Yeah.
Excellent. So, if there's any last question, thank you very much again, Gwen.
Yeah.
Very good presentation.
Thank you.
Then close for Gwen.